For me, it looks like we're live. Kyle, could you, okay, thank you. All right. Welcome, everyone. We have a very special seminar today. We're very grateful to our good friends and close colleagues from the Arase project to prepare us an update and present it in this hour, despite 12 hours difference between East Coast and Japan. We've been closely working and collaborating with the Arase project for close to 2 decades probably now, and that was a great collaboration while we had Van Allen probes going, and it's very good to see that this collaboration is ongoing along multiple avenues, including, of course, this seminar. Miyoshi is one of co-organizers of this seminar, so I will give the reins to him and allow him to introduce himself and the subsequent speakers. And thank you all for dialing in. Yoshi, it is all yours.
Okay. Can you hear me?
Yes, very well, Yoshi.
Okay, thank you very much. Thank you very much for giving a nice opportunity for us. So actually, we are very happy to share the Arase the result with the colleagues. Thank you very much for the continuous collaboration with the bar and probes colleagues. So that we had a very wonderful collaboration for a couple of years. So can you see my screen?
Yes, it is not in presentation mode yet, though. Okay, that looks great.
Okay, so firstly, we'd like to introduce briefly the overview of the Arase observation, maybe the 20 minutes, 25 minutes. Then, so our young colleagues, the Takahashi-san, the Matsuda-san, so that they are going to talk about some of the specific topics from the Arase and bar and probe the coordinated observation, especially for the wave particle interactions. So, okay, so we'd like to start this presentation. The title of this talk is the overview of the Arase observation, including the highlights from the conjugate observation with the bar and probes. So the conjugate observation with the bar and probes provide a very unique opportunity to find the inner magnetosphere, the several phenomena. So actually today we'd like to show you the examples of waves and the radiation belt variation by the 2 satellites measurements. So here is the contents of today's talk. So actually we'd like to show you some of the highlight result, focusing on the different wave particle interaction, the first mode wave, Whistler mode wave, and the EMIC waves. So we show some of the variation of the energetic particle with the wave particle interaction, and multipoint measurement will be very powerful to discriminate the temporal and spatial variation. And also we'd like to show the fast time scale phenomena, the cyclotron resonance, and Arase provided the direct evidence, the wave particle interaction. And the recent results, so especially for the collaborative observation between the bar and probe Arase, reviewed in the Space Science Review, and we are very happy if you look at this paper. And also the Arase paper lists are found in the ERG Science Center webpage, and please visit us, the ERG Science Center. Okay, so this slide indicates a geospatial system, and we are very interested in the dynamics of the wide energy plasma population from EV to more than MeV. And this is the collisionless plasma system, so the wave particle interaction will be very important to cause the dynamical evolution, the different energy of the electrons, the ions. So the Arase, this is the main objective of the Arase, and we'd like to understand what processes really contribute the enhancement of relativistic electrons, and what processes causes the dynamics of the geospace storms. So the Arase successfully launched the 2016, then the Arase start normal operation the March 2017, and currently the satellite continues the observation in the magnetosphere. So the firstly, I'd like to show you the average profile of the plasma sphere and radiation belt by the Arase. So here is the thermal electron density profile taken from the plasma wave data. And this is the top side ionosphere, and this is the plasma pose location. So the inclination angle of the Arase, the 30 degrees, so now the Arase covers the wide magnetic latitude from the -40 to the 40 magnetic latitude. And also the Arase has the receiver to measure the 10 megahertz. So now the Arase always measure the upper hybrid resonance waves from the perigee and apogee altitude. And right panel indicates 2 MeV electrons taken from the Arase, and we can see the outer radiation belt. So the very typical the population of the outer radiation belt and the plasma sphere. And this data indicates the 5-year data and error on time diagram, the plasma sphere, and the 2 MeV, the radiation belt, and the solar wind speed, and the CMH indices. So during this time interval, so that this is the declining phase of the cycle 24 and the early phase of the cycle 25. So that we didn't have enough chance to see the severe magnetic storms, but we see so many the high-speed corona hole streams. And we see the recurrent the variation of the plasma sphere, plasma pose shrink, then the recovery, plasma pose shrink, and the refilling. And also that we see the temporal the enhancement the outer radiation belt associated with the high speed the streams. So today we'd like to show you some of the highlights from the Arase observation by looking at the different wave particle interaction. So the first topics related to the MHD, the PC5, the pulsation, this is the waveform data that taken from the Arase. Okay, so this slide shows you the PC5, the interaction between the PC5 pulsation and the electrons. And this is the interval, so the Barren probe was the dusk side and Arase was the dawn side, and both satellite measures the almost same the L-shell region. So the panel indicates 40 minutes data, and color indicates a different energy electrons from 500 keV to the 2.5 MeV, and we can see the modulation associated with the MHD first mode pulsation. So the Arase also measure the electron modulation, the almost same energy range with energy dispersion. So now that this modulation taken the far away from the Arase location, and also the Arase didn't measure the MHD wave pulsation. So looking at these data and also the combined analysis with the ground-based data, that we identify the M number of the plasma waves and the modulation region between the MHD waves and the electrons. And in this case, it's the wave particle interaction between the first mode wave and the drifted electrons that really is localized within the 1 hour local time. So now such the specification will be possible by the coordinated observation by the Barren probes and the Arase. So as a next topic, we'd like to show you the Whistler mode wave particle interaction, especially focusing the Whistler mode chorus waves, the electron acceleration, and the electron scattering the processes. So the first example indicates the direct evidence to indicate the electron acceleration by the Whistler mode waves. So here is the 5 minutes data, and this is the frequency, and we can see the upper band chorus waves, and we see the burst of the upper band chorus waves. And the bottom panel indicates the electron energy and pitch angle, 10 keV, 20 keV, and 30 keV, and we see the temperature anisotropy like this. And 40 seconds later, so we see the enhancement, the 20 keV and 30 keV, the electrons associated with the upper band chorus waves. And this line indicates the diffusion curve. So now along the diffusion curve, that we see the enhancement, the 20 keV, the electrons. So that we believe that this is accelerated by the with remote waves. So after that, our colleagues conduct a data-driven simulation. So using the Arase observed wave data. So this is the result of the test particle, the simulation data using the Arase observed plasma waves. So we can see the 4 panels. This is the pitch angle and energy for the same format as the Arase data, 10 kV, 20 kV, and 30 kV for the 30 seconds. So we can see the enhancement, the electrons more than 20 kV, that this is the same as the observations. So bottom 2 panel, the time profile of the electron energy and the pitch angle. So looking at the green line, this is one of the examples, the test particle, that we see the rapid enhancement energy and the pitch angle within 100 milliseconds. So this is the phase trapping processes by the wave particle interaction. And this simulation identifies the nonlinear wave particle interaction really contributes rapid enhancement, the 20 kV and 30 kV electrons observed by the Arase. So another example indicates that with remote chorus waves actually causes the precipitation of the energetic electrons. So Arase, that we had the very nice conjunction with the ground-based measurements. So the ground-based optical measurement, the ground-based radar measurement, the ground-based riometer, and ground-based wave data. And this example indicates a nice conjunction with the ground-based optical measurements. So this is the Scandinavia Peninsula, and our colleagues installed all sky camera, this one, and green color indicate a footprint of the Arase satellite along the field line. And we can see the breakup or the aurora substorm and the omega band, and also the pulsating the aurora. So that in this time interval, so the Arase measures the modulation region near the equatorial plane. So the Arase detected the with remote chorus burst. So this is the 20 minutes data and frequency time diagram. So the Arase detected the chorus burst here. And the bottom panel is the electrons energy time diagram, the 10 kV and 50 kV. And we do not see any significant modulation with remote chorus waves. So the outside loss cone. But the Arase can capture the electron inside loss cone with a fine channel measurements. So this is the result of the electron measurements, the inside loss cone, the same energy range. So that we can see the one-to-one correspondence. I mean, the flux enhancement, the inside loss cone occur associated with the remote chorus burst. So that this result indicates the chorus causes the pitch angle scattering inside the loss cone. And this is the first direct evidence to indicate the actual scattering processes in the space plasma. And during this interval, the ground-based optical imager identified the pulsating aurora. So that the chorus burst causes the precipitation, then we see the pulsating aurora as a ground. So actually, the Arase, the colleagues study the pulsating aurora wave particle interaction pretty much. And this is another good example to indicate the relationship, the lower band chorus burst and the pulsating aurora. So here is 5 minutes data. And this is a kilogram. And we can see the periodical, the enhancement optical emission, that this is the pulsating aurora. And the bottom panel is the frequency time diagram, that is the 1 kilohertz. And we can see the lower band chorus waves. And we see the one-to-one correspondence between them. I mean, the chorus burst causes the main modulation of the pulsating aurora. And this red color indicate 5 seconds, and the bottom panel indicate 5 second data. And we see the modulation of the optical emission, that this is so-called internal modulation of the pulsating aurora. And the bottom panel is that we see the coupled rising tone, and the rising tone causes the internal modulation. So that the Arase and ground-based observation identify the multi-time scale interaction between the chorus and the electrons as predicted by our model. So another chorus wave particle interaction topics. So this is a nice observation by the Barn and probes and Arase along the almost same line. That is the Priscorpis paper. So this is a 8 seconds observation. The top panel is the frequency time diagram, the Barn and probes near the equatorial plane. And we see the chorus burst here, here, and here. And the third panel indicates the Arase measured the chorus burst at the magnetic latitude 20 degrees, and we see the same the direct rising tone, the chorus elements. So this is the first direct observation of the same the discrete rising tone chorus elements along the same field line. And actually, taking a look at the wave normal angle, the Barn and probe measured almost parallel propagation, while the Arase measured oblique propagation. That this is a very important result to understand the propagation of the chorus waves. And also the undercentric, so that they studied the lightning whistlers along the almost same line using the Arase data and Barn and probe data. So this is the Arase measure the lightning whistler at the L equal 2.5, and the Barn and probe measure the lightning whistler at the L equal 2.8, the almost same time. So this is a ray tracing result from the study, and with the red color indicate Arase location, and blue one was the Barn and probe location. So actually, the intercalibration between the Arase and the Barn and probes is realized by observation on the same the lightning strokes and propagated along the very similar the passes the two spacecraft. So using this data, so that they calibrate the relative amplitude and accuracy of the time tags. So this is the very nice the conjugate observation and contributes the intercalibration between the two satellites. And also we'd like to show the active experiments in space. So the Arase also collaborated with the DSX, and DSX is the active experiment. And this is the first result for the Arase detected the DSX transmitting the waves. So this is the time, and this is the frequency, and this is the frequency pattern of the DSX satellite. And the bottom two panel indicates the Arase is measured the frequency spectrum. So the VRF signal was successfully transmitted from the DSX to the Arase, and marking the first successful recitation of the space-to-space VRF signal. And actually, they tried the ray tracing to understand the propagation, and the results are consistent with the field and the propagation as expected from the linear cold plasma theory. So this is another good example to show the propagation of the Whistler model waves using the artificial VRF signals and Arase observations. And also we'd like to show you several topics about the the EMIC waves and the sonic model waves. So the first example indicates the EMIC waves that causes the MAB electron precipitation. So this is a very nice the multi-point measurements, the Arase and RBSP and the TEMIS and ground-based measurements. So this is the Earth, this is the noon side, the night side, the dawn and dusk side. So this is the Barn and probe, and this is the Arase, and this is the TEMIS, and this is the ground-based Antarctica base. And this is the Arase measured EMIC wave, and RBSP the wave observation, and ground-based observations. So during this time interval, so the Arase and the ground-based observation detect the EMIC waves, and we discussed the localized EMIC relativistic electron interaction that takes place. So this is the phase space density profile as a function of the L0 region, and we can see the localized depression of the phase space density. That means the EMIC waves that contribute the localized loss of the MeV electrons. So such the localized depression of the MeV electron by EMIC waves, the consistent with the simulation study, the Uri splits. But anyhow, such the multi-point the measurement identify where and when such the electron precipitation that takes place. And also the Arase contribute the direct measurement of the generation of the plasma waves. So this is a conceptual sketch to indicate the wave particle interaction. Here is the EMIC waves, and this is the gyrating the proton. And this is the magnetic field vector, and this is the velocity vector, and this is the theta, the phase angle. The theta means the relative phase between the wave magnetic field and the velocity vector. And Arase directly measure the phase differences. So for example, this is the falling tone, the EMIC waves, this is the time and this is the frequency, and we can see the falling tone here. And during this time interval, so that we detect the proton count as a function of the theta. And we see some of the significant modulation, the proton count, that means the proton hill. So according to the nonlinear theory, the proton hill contributes the falling tone, the EMIC waves. So that this is the first direct evidence to indicate the formation of the proton hill in the velocity space, and actual the falling tone can be observed. And also we conduct the same analysis for the sonic model wave and EMIC waves. So this is the 5 minutes data, and the panel indicate the frequency time diagram, the sonic model wave and EMIC waves. And this is the energy time diagram, the proton, and 100 eV, the 1 keV, and we see the heating of the 100 eV, the ions with the temperature anisotropy. So that we guess the sonic model waves, the heat, the protons, then the proton generates the EMIC waves. So that in order to identify such the energy transfer processes between the particle and the waves, so that we conduct the calculation, the velocity vector of the electric field of the plasma waves. I mean, the inner product, the E dot B. So the firstly, we try to calculate the E dot B for the sonic model waves and ions. So the heat is the time, and this is the E dot B, and we can see the positive the E dot B. And the positive E dot B means the sonic model wave, the heat, the ions. So the same time that we conduct the calculation for the E dot B between the ions, the EMIC waves, and the signature is a negative, and negative means the ions that generate the EMIC waves. So now the sonic model waves, the heat, the 100 eV ions with the temperature anisotropy, then the temperature anisotropy generates the EMIC waves. So such the cross energy coupling processes via the wave particle interaction are realized by looking at the phase differences, the electric field, and the velocity vector. And also we'd like to mention here for the intercalibration between the Arase and Barren probes, that this is another important topic for the collaboration between the Barren probe and the Arase. So this data indicates the electron energy and the flux, and the black one indicates the Magguy's data, and orange indicates left instrument, and other color indicates the Arase, the measured electron data. And we can see the very nice, the electron energy spectrum. So that this data taken from the CES cloud PL. And this is the Magguy's data. This is the Arase data. We also see the very nice correlation between them. And also just several the colleagues that try for the intercalibration between the Arase and Barren probes. And thank you very much for the very helpful comments for the calibration and also the realization, the intercalibration. So that this is a very unique opportunity and very helpful for us to improve the quality of the particle measurements. Okay, finally, we'd like to mention here how to get the Arase data. So all data, all satellite data, the ground-based data, and the modeling data archived in the ERG Science Center and open to the public. And also we developed the plugin software for speeders and PySpeeders. And instruction can be available on the YouTube channel. So please visit us, the ERG Science Center, to have the Arase data. So currently the Arase observed in the magnetosphere from the 2017 to the present, and the Barren probes start observation the 2012. So this is the long-term data from the 2010 to the 2024, and the Barren probe the data and the Arase the data. And we had the nice overlap the interval for the 2.5 years, And this is a very unique the interval, for example, the conjugate observation and also the intercalibration. And using this overlap time interval, that we can derive the uniform data set covering the whole solar cycle. So that this is a unique data set to study the inner magnetosphere. Okay, so this is summary of this talk. So firstly, the Arase team that appreciates the great efforts to the bar and probe the teams to realize the collaboration, including the intercalibration between the two satellites. And many collaborative observations between the bar and probe and Arase provide many science outputs. And we'd like to continue the digging out good conjunction events between the bar and probe and Arase and ground observation for various phenomena. And combine the data sets of the bar and probe and Arase that really contribute to the understanding the whole cycle variation of the inner magnetosphere. And also that we are interested in the discussion about the future satellite and the ground-based observation project because so the Arase mission extension until the 2032 has been approved by the Space Agency. So now the Arase satellite contribute the observation the cycle 25. So that we look forward to the hard collaboration with the bar and colleagues to understand the dynamics of the inner magnetosphere and the future inner magnetosphere mission. Okay, so this is my presentation. And Sasha, so maybe we continue the presentation by young colleagues.
I agree. Thank you so much, Yoshi. What a wonderful presentation and so many outstanding results. But let's hold the discussion and questions until the end of all talks. So yeah, please
okay.
go.
Okay. Takahashi-san, can you hear me?
Yes, I can hear you.
Okay, so the previous slides and more presentations.
Okay. So I just write.
I'd like to introduce Naoko Takahashi-san briefly. So Takahashi is a young colleague, and she works at the National Institute of Computer Telescope. So this is the national agency for the space weather. So she studied the wave particle interaction using the Arase and bar and probe data. And also she conduct the global MHD simulation and compare with the observation. Okay, so Takahashi-san, please start your presentations.
Okay, so thank you for introducing me, Miyoshi-san. So and thank you for inviting me. So I'm presenting about the relative contribution of waves to the radiation belt variation during the May 2017 storms. So this paper has been already published to JGR. So if you are interested to our result, so please check on this paper. So I'll now start from the briefly introductions. So our focus, we are focused on the radiation belt in the radiation belt dynamics in the Earth's inner magnetosphere. So in the radiation belt, maybe electron fluxes enhanced during the recovery phase of magnetic storm like this, and when electrons inducing from the plasma sheet, the electron accelerate up to the several hundred keV electron volt due to the transport by convection electric field. However, in the radiation belt, maybe electron fluxes are also enhanced. So how electron accelerate up to electric energies. So the previous studies clarifies that the electromagnetic wave makes a significant contribution via wave particle interactions. So there are two acceleration mechanisms. One is adiabatic process, radial diffusion by UF waves, which resonate with electron drift motions. The UF waves usually enhanced by the solar wind dynamic pressures or Kelvin-Helmholtz instability, and also UF waves enhanced by the ring current instability by substorm injections. Second acceleration mechanism is non-adiabatic, the local acceleration by Hoyser mode waves, which interact with electrons via cyclotron resonance. The Hoyser mode chorus enhance the temperature anisotropy of 10 keV electrons, and the electron density distribution can cause excitation of Hoyser mode waves. And the previous study also clarifies the magnetic field line contribution encourages non-linear wave growth and then the generates chorus waves. So in this study, key question is which contribution is dominant. First question is when and where UF waves and Hoyser mode chorus contribute to the net change of relativistic electron flux. Second point is what controls the wave evolutions. So we focus on the May 2017 magnetic storms, and we used the Multipoint spacecraft, actually the Arase satellite and Barnum probe and so in this point, we compare the time variation of UF waves and Hoyser mode chorus and compared to the enhancement of MEV electron flux. So actually, the Arase satellite is post-midnight, and the Barnum probe is around the dusk side. The second point, we use global MHD simulations, but that's with CRCM, so that we aim to clarify the global distribution of waves and relative parameters. So this is our observations from the Barnum probe speed in the dusk side. And this is a summary of the 4 magnetic storms. And we focus on the recovery phase, this box. In the early recovery phase, the UF waves enhanced at wide shell, but rapidly decaying. On the other hand, the Hoyser mode chorus is not enhanced at this. And in the early recovery phase, the MEV electron flux is enhanced at wide L shell. On the other hand, in the late recovery phase, around here, the UF waves is not enhanced. But on the other hand, Hoyser mode chorus enhanced at extra go 5 or 5.5 here. And in the MEV electron fluxes enhanced also around here. And this is Arase satellite observations and in the post-midnight and in the early recovery phase, and UF waves enhanced and L go 5, and Hoyser mode chorus is also enhanced at L go 4, and the MEV electron fluxes is both increase and decrease due to the including DST minimum at the early recovery phase. And on the other hand, late recovery phase, UF wave is certainly enhanced at low L shell. However, the Hoyser mode chorus enhanced at L go 5, and MEV electron fluxes at also the L go 2 locations. Here and here. So that we focus on the specific waves, and we focus on the UF waves, what controls the wave occurrence. So this is a wave summary of the wave power and the relative power and compared to the Preston level. This 3 panel shows the Barnum probes. This 3 panel shows the Arase satellite, and this is a solar wind picture from the discovered satellite. And in the early recovery phase, the UF waves in the PC 5 frequency range are enhanced both on the dusk side and night side are here and here. In the night side, this result includes a sudden enhancement associated with the substom injection in the surrounding dynamic pressure, enhanced only at 2 or 4 megahertz. So the observed UF waves in the lower frequency band may be driven by the solar wind disturbance. However, actually, the higher frequency band is also enhanced. So this may be caused by the internal instability, such as ring current instability. In the late recovery phase, UF power is relatively small compared to the early recovery phase. And the UF waves in the higher frequency range and 10 megahertz are also seen, especially the Arase satellite. This is a Hoshiyama mode chorus. And the left panel is the Barren probes, and the right panel is Arase satellite. And this is a power spectrum. And the second panel shows chorus wave power. And this is magnetic field, background magnetic field variations. So the last panel shows hot electrons flux and anisotropy, and in the dusk side, and the large anisotropy of hot electron is still like here and around here. And we also find the time variation on background magnetic field corresponding to the Hoshiyama mode chorus variation is seen only on the dusk side. Here, other that there is not seen such fluctuations. And there also finds no fluctuation in the cold electron density. So this is an observation summary, and we focus on the recovery phase. And in the early recovery phase, UF waves is UF wave power is active, and on the other hand, in the late recovery phase, not active. The Hoshiyama mode chorus, it depends on the MLT coverage, but the late recovery phase, Hoshiyama mode chorus is active, and so what controls such waves? For the UF waves, lower frequency frequency waves is driven by the solar wind dynamic pressure enhancement. On the other hand, higher frequency range and maybe internal instability and caused. And the Hoshiyama mode chorus in the night side, the electron anisotropy generates Hoshiyama mode chorus, but in the day side or dusk side, and magnetic field configuration also contribute to the enhancement of Hoshiyama mode chorus. In next, we'll check the global distribution of wave contribution using the global EMIC simulations. So we use waters with CRCM. This model is strongly affected by the solar wind. The top 3 panel shows the UF wave power, the main phase and early recovery phase, and the late recovery phase. In the global enhancement of UF waves during the main and early recovery phase, but the late recovery phase, UF wave is not enhanced. And this is a toroidal mode. And in the toroidal mode, we find the same distributions in toroidal mode. In the second second 3 panels shows the electron anisotropy and the 20 or 16 keV. And the region where electron anisotropy is large, shifts towards dusk, in the main phase around the day side, and then in the early recovery phase, eastward shift, and then the late recovery phase at midnight. So this is corresponds to the observations. So finally, the last three panels show the magnetic field curvature, and we find the small magnetic field curvature at the day side, so which means which is a shows the excitation of day-side chorus with nonlinear process around here. So particularly, we focus on the temporal variation of magnetic field curvature. We pick up the RBSP coverage around here, and then the calculation of magnetic field curvature by this formula, and by the simulation. In simulation, we averaged 200 grid points. And this is a result. And the top panel shows magnetic field, background magnetic field variations. And this panel C, it shows magnetic field curvature, and this two panels shows the observation from the RBSP, and the magnetic field curvature varies in time during the late recovery phase, and the oscillation period is around 15 minutes. This is close to the oscillation of the observed horizontal mode chorus. And magnetic configuration affects the day-side chorus in the outermost sphere. So from the previous results, so this supports the present result. So this is final slide of the summary of this study. And first key question is when and where UF waves and chorus contribute to the net enhancement of MEB electron fluxes. And the answer is the timing of wave contribution is different. And the UF waves contributes mainly early recovery phase. On the other hand, chorus depends on magnetic local time. And the second key question is what controls the wave evolution. In the UF waves, in the early recovery phase, particularly in the lower frequency range, solar wind and pressure enhancement contributes to the enhancement of UF waves. And on the other hand, chorus, mainly the electron anisotropy contributes to the wave evolution. However, we can conclude the magnetic field line configuration could also affect the evolution of chorus waves, particularly in the day side. So that is my studies presentations. Thank you.
Thank you, Takahashi-san. Okay, maybe we move to Matsuda-san's talk. Matsuda-san, can you hear me?
Yes, I can hear you. Can you hear me?
Yes. Okay, please share your slide.
Okay.
So I'd like to introduce Matsuda-san too. Matsuda-san is the Arase young colleague. So he's the data manager for the PWE, the plasma wave instrument, and now he works at Kanazawa University. Okay, Matsuda-san, we can see your screen, so please go presentations.
Okay. So sorry, please wait a moment. The Zoom is sorry. So can you see my screen now?
Yes, we can see.
Sorry, so my Zoom doesn't work well now. So I try to share my screen again.
Okay, now we can see your screen.
Yeah, can I?
Okay, yes, looks good.
Okay, thank you very much. Sorry, there is another error message from Zoom. So how should I do?
Now we can see your screen.
Yeah, sorry, please wait a moment. So can I make a presentation using this this
Yeah,
board?
it looks good like this
Yeah.
as well. Please go ahead.
Thank you very much. So hello, I'm Shoya Matsuda from Kanazawa University, Japan. I'm grateful for such a nice opportunity to share our study. Today's my talk is an international collaborative study with the US and Canadian colleagues. The title is Multipoint Measurement of Fine Structured EMIC Waves by Arase, Barren Probe A, and ground stations. So, as you know, EMIC wave is important plasma wave that controls energetic ion precipitation and relativistic electron loss in the radiation belt. Many studies have examined the statistical analysis of EMIC waves using long-term measurement data and investigated the global distribution of EMIC waves in the magnetosphere. On the other hand, several studies have examined the spatial scale of EMIC wave source region. For example, Sakaguchi et al. 2015 statistically analyzed the patchy size of isolated proton auroras observed by a ground optical instrument. And they estimated the size of wave-particle interaction region due to EMIC waves. So in this study, we introduced an EMIC wave event detected by Arase, Barren Probe A, and 2 ground stations. By using these in situ measurement data, we discussed the size of EMIC wave source region and the spatial extent of a wave propagation duct connecting from space to ground. So first of all, I will show the data set and configuration of the event. We present the results of a coordinated observation of fine structured EMIC waves on 18 April 2019. For Arase data, we used the PWE EFD instrument and MGF instrument data to analyze the EMIC wave spectrogram. And we also used the LEPI, low energy ion detector data to analyze pitch angle distribution of proton and helium ion. For RBSP-A data, we used the M-physis magnetometer data to analyze the EMIC wave spectrogram. And we also used the ECT HOP measurement data to analyze pitch angle distributions of low energy ions. And as the ground measurement data, we used the induction magnetometer waveforms measured at the Gakona station, which is one of the stations of the Japanese P-Wing magnetometer project, and data from Dawson station of the Canadian Charisma magnetometer array. So the right figure shows the magnetic footprint of Arase and RBSP-A at an ionospheric altitude for the time interval from 0 to 3 UT on this day. The Arase was crossing a wide L-shell range from 7.8 to 1.9, while RBSP-A was orbiting at almost the stable L-shell region from 5.0 to 5.6. So these panels show the results of simultaneous plasma wave observations. From top to the bottom, we showed the electric field observed by Arase, magnetic field by Arase, magnetic field by RBSPA, and magnetic field by P-wing, and the magnetic field by Charisma. And the last three panels indicate the orbital information of Arase and RBSPA. At the timing of this vertical dashed line, these two satellites were orbiting at almost the same magnetic local time and the same air shell at 5.7. The magnetic latitude of Arase was about 30 degrees, whereas RBSPA was in the equatorial plane. So, as shown in the top 5 panels, fine-structured helium band EMIC waves were simultaneously observed at the 4 locations in the 2 frequency ranges. In this study, we called lower one as lower frequency EMIC wave, and the higher one, this one, as higher frequency EMIC wave. The EMIC wave intensity in the mid-latitude region observed by Arase was significantly larger than that in the equatorial region measured by the RBSPA, especially the lower frequency EMIC wave measured by RBSPA was clearly weak compared to the Arase measurement. So the time frequency spectrogram measured by the RBSPA, Gakona, and Dawson stations were quite similar during the entire event. On the other hand, wave spectra observed by Arase was different from others. So the left bottom panel shows a cross-section of the time frequency spectrogram measured by the Arase and RBSPA. So focusing on the timing of the field line conjunction, the frequency bandwidth of the observed EMIC waves by 2 spacecrafts were almost the same. So except during this time interval, the frequency bandwidth of the EMIC waves observed by Arase is much broader than the RBSPA result. So I summarize these results on the map of this spacecraft footprint. If we overlap the wave observation timings on this map, we got this figure. The bold purple and bold light blue lines indicate the locations where lower frequency EMIC waves were observed and the higher frequency EMIC waves were observed, respectively. The purple shaded region from here to here denotes the air shell region where the lower frequency EMIC waves were observed, and the light blue shaded region from here to here denotes the air shell region where the higher frequency EMIC waves were observed. So by comparing the observations by Arase and RBSPA, we found that both EMIC waves were confined to narrow air shell ranges. Using the Chigonenko 89 magnetic field model, we both these narrow air shell ranges correspond to about 185 kilometers latitudinal width at an aurora altitude of 100 kilometers. And please remember that a weak lower frequency EMIC wave was observed by RBSPA in a limited time interval. So focusing on the trajectory of RBSPA, the trajectory was traversing the edge of the purple shaded region. That's why a weak lower frequency EMIC wave was observed in this limited time interval. So the broadband EMIC waves were observed only by Arase. Because these were not observed by RBSPA and 2 ground stations, we conclude that the wave propagation duct existed in this narrow L-shell range. Using the Chinganenko 89 magnetic field model, it was about 80 kilometers at an ionospheric altitude. So this scale is smaller than the EMIC wave activity region estimated in this study. So this page shows the thermal ion observations by RBSPA and Arase. So as shown in the panels B and C, there are 2 clear signatures of ion heating. One is the proton heating with the almost the parallel pitch angles, and another one is the thermal helium ion heating with the almost perpendicular pitch angles. And bottom panels show the phase space densities of protons as a function of the local pitch angle observed by the Arase LEPI ion instrument. As shown in the panels G and H, clear signatures of less than 100 eV proton heating with local pitch angles around 30 and 150 degrees were observed. The local pitch angle of 30 degrees at Arase corresponds to 17 degrees equatorial pitch angle by considering the conservation of first adiabatic invariant. Therefore, we concluded that both Arase and RBSPA measured the same enhanced proton distribution within a narrow L-shell range. So this is a summary of my talk. In this study, we successfully measured the latitudinally propagating EMIC waves by Arase, RBSPA, and 2 ground stations. We concluded that the spatial extent of the EMIC wave activity region was about 185 kilometers latitudinal width for this event. And the spatial extent of the wave propagation duct was about 80 kilometers latitudinal width. So this is the last slide. This is just an announcement. So our work has already been published in GRL. So I'm very happy if you visit this paper, this website. Thank you very much.
Thank you very much, Matsuda-san.
Yes,
yeah, these are, the presentation our side. Sorry, so that takes already 1 hour.
No, that's great. So we started a few minutes late, and there's nothing to be sorry for. Very interesting talks with outstanding science results. Perhaps a couple more quick questions before we adjourn. I know that we're turning into a new hour, which means that folks probably need to go to a different meeting. But we have time for a couple of quick comments or questions. I would like to ask a very quick question to you, Yoshi. You showed very interesting observations of onboard Whistler chorus waves and electron intensities inside the atmospheric loss cone, and as well as some conjugate auroral measurements in one of your slides. I was wondering if you also looked at relation of some of these chorus waves with bursty bulk flows or lower energy ion injections.
So maybe this slide.
Yes.
Okay, so actually these are direct evidence to show the chorus waves causes the precipitation inside the loss cone. And these chorus waves generated the injection during this time interval. So the temperature anisotropy of the injection contributes the first generation, maybe the linear, the growth, then we see the subsequent, the nonlinear, the processes. So actually the very interested in the how the burst bulk flow contributes such the the injection processes as well as the subsequent the chorus waves, and finally the precipitation into atmosphere as the pulsating the aura. So the such the relationship, the connection, the
Right.
really very interesting.
It's very interesting. We'll be highly keen to work a little bit more with you, comparing it to some of our modeling results, but we can talk about that offline. More comments? Thank you, Yoshi. More comments or questions?
So Miyoshi, I have this question about just like the same topic there. You very clearly show the correlation. As to I'm wondering what was the limit. We know the chorus wave was caused by supposed to be by this lower energy electrons up to keV also, but here shows very close to be that range. The 10 keV precipitation in the last cone was so energy is from this 10 keV is gives to a chorus wave or contributing to generating chorus wave, or not. Your interpretation right now here is a chorus wave caused that precipitation. But I bet for low energy electrons, you're probably going to see something similar as well, just because anisotropy of this lower energy electron, because anisotropy instability, so they can cause the chorus wave.
Okay. Actually, firstly, we suppose that the few keV, the 10 keV electrons simultaneously contribute the generation of the chorus waves, and simultaneously the precipitation observed, because actually the electron hole formation is essentially for the nonlinear chorus generation, and hole contributes the precipitation itself. And also we are interested in the lowest energy, the low energy component electrons. So this instrument measures the electrons more than 7 keV, but the Arase has the different electron sensor, less than 20 keV to the few 10 eV. And such the electron instrument LEPE almost has a loss cone, the resolved loss cone. And actually our colleagues looked at the electron flux inside the loss cone for the low energy component. So actually they identified the upper band chorus wave and ECH waves. So electrostatic waves that contribute the precipitation, such the low energy electron, the few hundred eV to maybe the 3 keV or something. But the 3 keV, the 7 keV, the marginal ECH wave and upper band chorus wave and the lower band chorus wave contribute to the such energetic population, very complicated. So some cases the lower band chorus waves are dominant, but some cases the ECH is dominant. So maybe that depends on the situation. But anyhow, so the Arase, can observe the wide energy electron precipitation inside the loss cone.
Okay.
Thank you.
Great, thank you. More comments or questions?
This is Guru.
Of course, Guru, go ahead.
I have a quick question. Yoshi, it was a great talk. I really loved it. I enjoyed everything. One quick question is, do you see any correlation of the state of the radiation pulse with reconnection or large-scale reorganizations of the magnetotail?
And actually, there are several conjunction events between the Arase and the TEMIS or the MMS so far, but we didn't have the much the observation to identify the causal relationship between such the tail signature and inner magnetic phenomena. So Sasha pointed the same thing. The bursty black flow contribute the injection, and we see the chorus waves. So the further study is very necessary for how such a tail dynamics contributes the inner magnetosphere, and what happened in the magnetosphere, the generation of the waves and the resultant acceleration of the electrons as well as the precipitation. The very interesting, maybe the conjugate observation between the TEMIS and the Arase, the MMS and the Arase, and of course, the Arase, the Barren probes, the MMS. That will be the very important.
Thank you.
Okay, thank you.
Please go ahead and mute and ask your question.
Okay, thank you. Thank you very much for the great presentation. I just have a quick question. Like the event you just showed for the oblique coarse waves, did you see any interesting flux dynamic in that event? Because the coarse waves are like very oblique from both Van probes and Arase. Thank you.
Yes, thank you very much. Yes, that's a very important point. So this Chris Colpit's paper was very nice. So that we both satellites identify the same porous burst, but the wave normal angles are different. So currently our colleagues are looking at the electron data, how the electron distribution modified with the coarse wave particle interaction. So actually during the propagation, the normal angle changes. I mean, it becomes oblique. Of course, the resonance condition also change. So that we may see some of the signature that depends on the wave normal angle. So that is really the ongoing stuff. Yeah, thank you very much. Very nice, important point.
Right, thank you. Do we have more comments or questions? If not, let's thank our speakers again for outstanding talk, despite a very subsequent time difference. So hope they'll be able to sleep in a little bit since tomorrow is a weekend after this. Thank you all for dialing in, and we will do this again in 4 weeks. We will have a seminar dedicated to radiation belts across the solar system. So please stay tuned for that announcement. Thank you.
Okay,
Bye.
thank you very much.